Moving on to another important actuator used in robotic applications, which is electric motor. And as we know, electric motors are the most commonly used actuator for robotic applications. So because of the reason of excellent controllability and minimum maintenance. Excellent controllability means we will be able to control the torque, the RPM, and even the angle of rotation of a DC motor much easily. And the maintenance required for a motor will be much lesser than that of a pneumatic or hydraulic actuator. And there are basically three types of motors used for robotic applications. One is a DC motor, then servo motor, and finally stepper motor. And we will be studying in detail about these various types of motors in the upcoming slides. And before that, we need to know the basic working principle of a motor. So it is common for all the three type of motor. And DC motors works based on the Faraday's principles, Faraday's laws of electromagnetic induction. That is, when a current carrying conductor is placed in a magnetic field, it will experience a force which is normal to the plane formed by the magnet and the current. Here you can see a magnetic field established from say left to right, and there is a current carrying conductor which is capable of moving or rotating with the axis of rotation normal to the direction of magnetic flux. Here, from our knowledge, from our previous knowledge, we will be able to obtain an equation for torque of a motor, Tm of t equal to Km Ia of t, where Km is a motor torque constant and Ia of t is armature current. That is, the torque produced in a motor is proportional to the current flowing through the armature. Current and torque is directly proportional with the proportionality constant Km. And now moving on to developing an expression for back EMF, we know from the Faraday's laws itself, when the armature rotates inside a magnetic field, it induces a voltage in the armature due to Faraday's laws, or it's again called generator action. The voltage generated will be proportional to the angular velocity of the rotor, and the direction will be in such a way as to oppose the applied input voltage. So the applied input voltage and the induced EMF will be in direct opposition, and the expression for induced EMF EB of t will be equal to KB omega of t, where omega of t is the angular velocity and KB is the voltage constant. And because of this reason, the net voltage inside armature will be the input voltage minus induced EMF, that is V in of t minus EB of t. Thereby, the resultant current, armature current IA of t, will be equal to the net voltage divided by its resistance, that is V in of t minus EB of t divided by RA. RA is the armature resistance. And as the motor velocity increases, the back EMF also increases and the current available in the armature decreases. That means the motor current will be maximum, or the armature current will be maximum on the start of a motor, and as the armature takes or increases its velocity, angular velocity, or as it increases its RPM, the current slowly decreases, the armature current slowly decreases. And as the armature current decreases, from the previous equation we just seen earlier, the equation of a torque, the torque is directly proportional to armature current. And since armature current is decreasing as speed increases, thereby there will be a resultant decrease in the torque of a motor, or we can say a motor's torque will be maximum on the start of a motor, and it will slowly decreases as the motor progresses in terms of velocity. In the upcoming slides, we will be going to see the 3 different types of motor and the unique features of each in detail.